14.6, we're going to use a lot of perfect squares. We need to really understand and know our perfect squares and to be able to use them as factors. So to begin this homework assignment, I'm going to go down the side here and just list my perfect squares. And then today, as we go through each problem, we'll have a list of perfect squares to select from as we do each problem. So for today's lesson, I would say if we have the perfect squares up to 10 squared or 100, we should be fine today to be able to solve each problem. So in number 2, I want the square root of 144. Here I said probably up to 100 will be good, and then the first one is 144. So if I keep going, the next perfect square is 121, that's 11 squared, and then 12 squared is 144. So the square root of 144 is 12. And the reason why it's 12 is because 12 times 12 is equal to 144. Now, in just a moment, we're going to actually write plus or minus 12 because when we solve a quadratic equation, we're going to get two answers. We're going to talk about that in a minute. But here, they just want me to do the square root of 144. So we're going to say that the principal square root or the positive square root is 12. All right, number 4. 12 is not a perfect square, but it does contain a perfect square. Notice that 4 is a factor of 12. So I can rewrite the square root of 12 as the square root of 4 times the square root of 3. Taking the square root of 4, that gives me 2 root 3, or 2 radical 3. Number 6, the square root of 45 is not a perfect square. Square root of 49 is, but the square root of 45 is not. However, the square root of 45 contains a perfect square, and I can break this down into the factors, the square root of 9 times the square root of 5, and the square root of 9 is 3 times radical 5. Let's see, radical 54. I'm thinking of a number that goes into 54 that is a perfect square. I think the number 9 again does go into 54 evenly. It goes into 54 6 times. So I have written the square root of 54 as the factors, the square root of 9 times the square root of 6. And then I'm going to multiply it by this 5 at the very end. So I have 5 times 3, the square root of 9 is 3, times the square root of 6. And so 5 times 3 is 15 times the square root of 6. Now in numbers 9 through 12, they want me to give an approximate value. And the best way to do this is to grab your calculator and to plug in the square roots of each of these numbers to get what the approximate value is to the nearest tenth. So I'm going to use my second function. X squared gives me the square root of 37. And I'm going to get in the habit of closing my parentheses. And to the nearest tenth, we are going to write that as 6.1. So when I say approximately, I use the symbol approximately 6.1. And let's take a look at the square root of 27, which is approximately 5.2. Now, when we think about approximating square roots, we can think about a number line. And so on my number line, radical 37. Radical 37 is in between radical 36. It's very close to radical 36, which is 6. And radical 49, way down here, radical 49 is 7. So we can see it's somewhere in between 6 and 7, and it's much closer to 6. It's just right here next to 6. So it makes sense to us that the square root of 37 is 6.1. And also radical 27, if we were looking at a number line, here's radical 27. So radical 27 is very close to radical 25. So it's going to be a little bit more than 5, but definitely less than radical 36, which is 6. So radical 27 has to be between 5 and 6. It's much closer to 5. So again, that makes sense that the square root of 27 is about 5.2. Now, in number 14, we're actually solving for m, and it's asking me to find the roots. And so here's where I need to remember my plus or minus. Let's say I have the equation m squared equals 4. M squared equals 4. So when I take the square root of each side to undo my square term, I'm going to take the square root. Again, m is equal to plus or minus 2. Now, why is that? Well, there's a couple of reasons. Positive 2 times positive 2 is 4, and negative 2 times negative 2 is also positive 4. But what I want to remember is I have a quadratic function. Quadratic function. So when I graph a quadratic function, for example, if I were to graph the equation y equals x squared minus 4, x squared minus 4, I get two roots, or I get two x-intercepts. One is at positive 2, and one is at negative 2. So I just want to remind ourselves what we really have here when we are solving something like m squared equals 68. So as I solve number 14, I'm going to begin by taking the square root of both sides. And again, m is equal to plus or minus radical 68. And then I'm going to go back here and look at my list. And I'm going to see if any number in my list of perfect squares goes into 68 evenly. I don't think 9 does. Maybe 4. Let's try 4. Let's see. 68 can be divisible by 4. Let's see. 4 goes into 6 once with 2 leftovers. And 4 goes into 28 17 times. So, yes, radical 68 does contain a perfect square. So let's go back down here and let's break down radical 68. So radical 68 can be written as the square root of 4. Oops, I've already forgotten. What was that? The square root of 17. And so m is equal to plus or minus 2 root 17. Number 16. So to extract the root, I'm going to take the square root of both sides. And that gives me x plus 8 is equal to plus or minus radical 29. And to isolate the variable x, I'm going to subtract 8 from both sides. So when I subtract 8, it becomes negative 8 plus or minus the square root of 29. divide by 25 as I think about quarters. And I want to know how many quarters are in $1.75. How many quarters are in $1.75? So I have 4 quarters in $1, 3 quarters in 75. So 4 quarters and 3 quarters would be 7 quarters. 7 quarters, 7.25 is 1.75. All right, to simplify radical 80, I noticed that not only does 4 go into 80, but 16 also goes into 80. So in the event that you have 2 perfect squares, you want to select the higher perfect square so that you only have to simplify it once. So I'm going to break down radical 80 into radical 16 times radical 5. So in number 24, I want to begin with the function f of x equals negative 3x squared, and then to that I need to make some changes. So I'm going to call my new function g of x, but because I do want it to open down and vertically dilate by a dilation factor of 3, I need to begin with my a value as negative 3. So my dilation factor is 3, and we want it to open down, so I have negative 3 for my value of a. Now it says I want to translate 4 units right. So that means x plus 4. I'm going to translate, to the right would be x minus 4. Let's do the opposite, x minus 8, so x minus 4. And then 2 units down would be minus 2. So my new function is a horizontal reflection of x squared. It is vertically dilated with a dilation factor of 3, and it's translated 2 units down and 4 units right.